last class we talked about chapter 4. Now, again, in chapter 4 we start to look at a second question in mechanics, which is dynamics. Basically, we try to explain motions here in this chapter, and the key here is Newton's 3 laws. Okay, and basically what Newton said was that force is the reason for the motion. And based on some simple argument and simple demonstration, we conclude that force is only related to acceleration, not to the other two kinematic quantities we learned from chapter 2 and 3. So, so we will, and then we say there's a simple relation between them. This F equal to ma. This is called Newton's second law, and there's also first law saying that when there's no force, the object stays at rest or in a constant velocity motion. That basically saying that the object has, every matter have something called inertia. This is like a property, intrinsic property of matter. They tend to stay with their status of whatever way they're right now. So if you want to change the status, you need to apply force. So, and in some sense, the first law can be viewed as a special case of the second law. When you take F equal to 0 from this equation, you got A equals 0. So when A equals 0, certainly is the object stays at rest or in a constant velocity motion. So in terms of solving problem, we don't really need the first law, but the first law provides us a starting point to talk about all these, and it kind of serves as a way to define inertia. So, and then we talk about third law. Remember this martial art question, right? You punch somebody, does that make sense? Because the forces are equal. But then the point there is, although the forces are equal, the spot that get the force are different. You know, some spots are stronger than the other spots. So if you punch like a stone, right, you're gonna hurt your fist. Well, the stone stay no problem. But if when you punch something like a fragile, like a, you know, then somebody's face or something, you know, then the result is very different. Your face is probably gonna be the stronger thing in there. Okay, so we're done with the 33 laws. Okay, now starting from today, this is some like very general introduction. Well, in order to really use the law, use them, especially the second law. Well, the third law is actually useful when you talk about like a two-body problem or many body problem, because there's going to be interactions, and the action and reaction are kind of a important concept. But for us, we will stay with a single body problem, because this is a little bit simpler. And to use them, we actually need to talk a little more specific. So today, let's start from the second law again. Okay. So we have F equals to ma. Okay, and well, the first thing we notice here is the mass here is definitely a scalar, but the expression, as we know, is a vector. So we need to put an arrow on top of it. So based on this, what do you think about the force? Is the force a vector or a scalar? You can send me a message, you know, let me know, what do you think? Let me take a look. Okay, there are two different kind of opinions. Some people saying it's a vector. Some people saying it's a scalar. Well, okay, there are two ways to see that. Okay, I guess everybody now saying it's a vector. So one is like, if you just look at the equation here, right? So on the right hand side, we have a scalar, basically it's a number times a vector. So this give us a vector. This is definitely a vector. So to have something equal to that as a vector, this thing itself pretty much has to be a vector as well, right? Do you agree? Well, we cannot have a scalar equal to a vector here, right? That would be weird. So and they actually equal each other. So this is actually a vector. Another way to see this is just think about some specific intuition. I mean, examples, right? If you apply a force or something, like say you push something, right? It's pretty natural that you can say that you're pushing this thing along one direction or another direction, you know. So direction definitely is kind of a natural part of the force itself. So the force is a vector, okay? So we need to put an arrow on top of it. So, and so force is a vector, okay? And this is actually why we need to spend the whole chapter talking about solving problem is Newton's law, because force is a vector. So a lot of stuff we need to do, like when there's more than one forces on the object, we need to use the vector way of treating them, you know, using the vector addition and the vector like component method, et cetera, et cetera. So these are all applied here. So that's why I'm saying that last chapter was kind of important when we talk about vector, because it's applied to this chapter as well. So force is a vector, okay? Now let's also talk about the unit of force, okay? So again, we can derive the unit using what we have on the right. So we know for the mass, the unit is, so let's say unit. So the mass unit is a kilogram. For acceleration, the unit is meter per second square, okay? So we have kilogram times meter per second square, right? So, so that basically is the unit for force, okay? But this is a pretty long expression, so to make it simpler, people call this Newton, okay? Or simply just N. So this is just to honor the person that did a great contribution to all of these. So from now on, we'll call it Newton, but you need to keep in mind, Newton is nothing but 1 kilogram times meter per second square. Okay, this is the same thing. Okay. So, okay, so this is about the unit. Okay, what else? And actually, in order to use this formula here, right, how do we use it? How do we explain motion, right? So basically, think about it, right? If you have an object, right, this object is there and then it's moving, right? We want to understand why it's moved this way instead of other ways. If you use Newton's second law, it means that you need to find the force on the object, right? And then from the force, you can get the expression immediately. And then from the expression, you can get the other things like how the velocity changes and everything, right? So this will be explanation for the motion. So in order to use this formula, well, normally there's more than one force on the object, you know, and they normally go to different directions, okay? So what we need to do first, before we start to use this second law, is we need to get we know what are the forces that we have, okay? So forces we have, okay? Without knowing them, without understanding those forces, there's no way we can use this second law to actually solve problem, to get the kinematics, okay? So in some sense, a main goal in physics is to figure out forces as we go into different kind of a sub-discipline or subfield. You know, when we talk about mechanics, we have some forces to talk about. When we talk about electromagnetism, we have other forces to talk about. And another word for force is interaction. These are normally mean the same thing, okay? So again, let me start giving you the big picture about interactions, okay? In this whole universe, it turns out that there are not too many kinds of interactions. It turns out there's a certain number of fundamental interactions, you know. There's a number for that. The number is not really large. Fundamental interaction. I don't know what this. Do you guys know the number? How many numbers of fundamental interaction we have? How many fundamental interactions we have? Do you guys know? Okay. Okay, there's actually just four kind of fundamental interactions, and they're basically gravity, And then we have electromagnetism. And then we have strong interaction. My whiteboard for some reason is not writing very well. And then we have weak interaction. So these are the four kind of interactions we have, okay? So, well, these two, strong and weak interaction, they exist only in very small length scales, like 10 to the negative of 15 meter or something. So they don't show up in the macroscopic scale. Well, gravity and electromagnetism are the two basic interactions that that kind of will control everything macroscopically, okay? And you may ask, why do we have four? Why not 5 or 6 or 7, okay? Well, it depends on how you look at it. It depends on how you categorize a interaction. So at high temperature, some of these interactions can be united to one interactions, okay? And when the energy is really high. When the energy is low, it becomes different. So anyway, this for just for like normal temperature scale we have, then there's like this 4 interactions. And this might sound a little crazy because, for example, when you push somebody, right, you feel like this is definitely not gravity and this is definitely not electromagnetism. So what kind of interaction it is? Okay, it turns out when you push somebody, like this person feels a force from you, it's kind of like electromagnetism, okay? But it's not a direct electromagnetic force because there's no charges here, but it's more like a, I mean, an advanced level, complicated level force that kind of worked as a multi-pole interaction. And also there's a quantum mechanics working here because the Pauli exclusion principle, there's, you don't want the two microscopic particles, they don't want to overlap. They don't want to go to the same state. So there's kind of give you a repulsion something. Anyway, we don't need to know too much about it, but just to have this idea that there's this 4 fundamental interactions, okay? So, well, although there's only 4 fundamental interactions, these interactions actually produce a lot of high-level interactions. That's, I mean, like combining effect and everything. So we'll mostly talk about these high-level interactions that exist in our everyday life in mechanics. So in this class, we need to go through, let's go through the forces that are important for this class. Okay, so the first one we have is called gravity, okay? And as we know, it is one of the fundamental interaction, right? But it's also like one of the important one we need to know for this class. So gravity. So what is gravity? It's very simple. So this gravity actually is governed by the, it's again not discovered, but kind of explained clear by Newton, okay? So he had a law called Newton's universal gravitational, universal law of gravitational attraction. So what this law says is something really interesting. So what this law says is whatever matter you have, whenever you have like matter, right? Let's say consider 2 different pieces of matter here, okay? 2 objects, okay? There's gonna be a universal attraction between these 2, okay? No matter what they are, okay? There's always gonna be attraction, okay? So the attraction given by one to the other, like we call this Fg here, okay? Fg equals to G times M1, M2 divided by R squared, where R is the distance between these 2 objects, okay? So this is the law. I mean, this is kind of the expression to calculate this universal gravitational attraction. And it's given by the constant G, called constant, I will explain what it is. And then M1, M2, which are the 2 masses of the 2 objects. And then we have this r squared in the denominator, which is the distance. So it's proportional to the mass of the two objects and the inverse proportional to the distance between them, okay? Well, this g here is a constant called gravitational constant, okay? So the value is 6.67 times 10 to the negative 11s, okay? Newton meter squared divided by kilogram squared. So that's this constant here, okay? And this law is very simple, as you see here, right? It's basically saying that whenever you have two matter, there's a attraction between them, and you can calculate this attraction. Well, based on our law of, Newton's third law, if there's attraction from object 2 to object 1, there's certainly going to be attraction from object 1 to object 2, right? They're just going to be equal to each other and opposite direction. So because the force of vector, right? Now, if you go back to this formula here, I forgot to say that if we put the arrow on top of them, right? There's going to be a negative sign here because they're going to be same in magnitude but opposite in direction. Okay, so now the first question you may wonder is, if that's true, why don't I feel it, right? I don't feel attraction from other people or other objects, you know? Like if I walk towards a building, I don't feel I'm attracted to it, you know? I don't feel a force pushing me, pulling me to the building or something. Or when I walk towards my car, right? I don't feel there's attraction from my car, pulling me to the car or something, right? So why is that, right? So it turns out the reason for that is essentially this gravitational constant here. So this force is actually a very small force, okay? So small that you wouldn't feel it. So let's try to give like a specific example to calculate, okay? So consider, for example, two students sitting next to each other. Like normally when students sit in the class, let's say the distance between them is roughly about 1 meter, okay? Well, they should have arms here, so. Okay, anyway, so these are my students. So they're staying 1 meter from each other. Now, for simplicity, let's also say they have pretty big mass, 100 kilogram per person. That's definitely a exaggeration. 100 kilograms is really large. It's like more than 200 pounds for each one of them. But that's an easy calculation because it's 100 kilograms is like a whole number. So if we plug these numbers into this, we can calculate the gravitational attraction between the two students. If you plug all the numbers in there, so 6.67 times 10 to the minus 11th times 100 from the mass of the first student times 100 from mass of second student divided by the distance, which is 1 meter squared, okay? Now, as you can see here, right, you have 6.67 times this negative 11 times 4, 10 to the 4th, so it's 10 to the negative 7th, okay? So you got a value like 6.67 times 10 to the negative 7th Newton, okay? Now, how big is 1 Newton, okay? 1 Newton is roughly 0.2 pound, okay? So it's a very small unit here, okay? So, basically this force here, 10 to the negative 7th, right? So you won't feel anything. If you sit in the classroom, you won't feel it from your neighbor, you know, this force. And by same reasoning, you cannot feel attraction from a building or a car, even though the car may have like a 10 times or couple, 20 times heavier mass here, bigger mass, but this 10 to the minus 11 is gonna kill everything. So even you won't even feel it from a mountain or something, okay? This force is still tiny, so tiny, you know, you don't feel it, okay? So there's only one gravitational attraction force, you actually feel it, okay? And you feel it every single minute, every single moment, okay? And that force actually play a critical role for everything we have on the Earth. Without that force, we won't be here. We won't exist at all. So that gravitational attraction is critical, okay, for the existence of human beings and all life on the Earth. Do you guys know what kind of force is that? What force is that? The force we feel every day? the one gravitational attraction we feel every day? Hey, you guys have no cameras right now, right? So that means you could answer your question, right? I mean, you can just talk because nobody will see you, you know. They just see a name or a picture or something. Or you can send me a message. Anybody?
Will you repeat the question?
Oh yeah, sure. I'm asking there is one critical gravitational attraction that's very important and you feel that attraction every day. What attraction is that? Okay, I got one answer. Oh, yeah. Yeah, gravity. Somebody just said gravity. Gravity, well, that's kind of a little bit vague because you could say gravity to all these attractions. But okay, now another answer like from the Earth or to the Earth, that is actually the important one. Well, friction is not, no, it's not a gravity or gravitational attraction. So the one that we actually we feel every day is the attraction from the Earth. Okay. Well, that attraction is certainly very important. Okay. Basically, without that attraction, we won't be kept on the ground. Okay. Because the Earth is rotating, right? Without the attraction, we will be all thrown away, you know, to the air. And I mean, to the space, right? And there's no air. There will be no atmosphere as well because it takes attraction to keep the air around the Earth. Without the gravitational attraction, the atmosphere won't be there. We won't be able to breathe, and then there won't be anything to block the ultraviolet light rays from the sun. So we will have like a very, very hot temperature when on the surface of the Earth facing the sun. Well, the other side will be really cold, and we won't have anything like water or anything. It'd be like a totally death. So that gravitational attraction is critically important for us. Okay, so and because that is important, we like to do some calculations about that gravitational attraction. Specifically, we like to calculate like the force on any object from the Earth. Okay, the gravitational attraction. Okay, so the way to do that is we'll just use the formula again. Gm. Okay, here I'm going to use capital M and lowercase m, and then r squared. Okay. Well, this is the radius of the Earth, and then this is the mass of the Earth. Okay. Well, this actually is not an easy job if you really think about it, right? Because Earth is not a single point; it's actually a gigantic volume here. So, strictly speaking, there's an attraction to the person from everywhere. Okay, on the Earth, you know, from the equator, from the North Pole, South Pole, everywhere. But so it's actually not an easy task to calculate the attraction given by the Earth. And it took Newton about 10 years to figure out the problem. He developed like integrals to do this calculation. But for us, because we don't require calculus, so we won't be able to talk about that. So we'll just quote his conclusion. His conclusion is the attraction can be considered equivalently as all the mass of the Earth located at the center of this sphere. So the distance between this is just the radius of the Earth. So that's what we're doing here. So we're using the radius of the Earth here and the mass of the Earth, okay? And then G, which is the gravitational constant, okay? And then the mass. So what we're gonna do here is, because we wanna calculate kind of universal formula, so we'll leave the mass of the person by itself. So, and then we'll go ahead and calculate this combination here, okay? So the way to do that is plug in numbers for the gravitational constant, 6.67 times 10 to the minus 11th, and then plug in the mass of the Earth, and the radius of Earth, and in kilograms and in meters. So what we're gonna do here is we're gonna just look it up, okay? So you can actually find this also in the book, okay, in your textbook, okay, mass of the Earth. So we have this one, see 5.97 times 10 to the 24th, okay? We'll just keep 3 sig figures because that's what we have. 10 to the 22nd, 24th. Okay. Now, same thing. We need to do radius here. I know the radius is roughly like 6,000 kilometers, but we want a little bit more than that, more accurate than that. Okay. Okay. There. Okay. So see, this is a number. Okay. So again, the Earth is not a perfect sphere. So it's a little bit aspherical, but it's pretty good. See, this radius and this radius, the equatorial radius and the polar radius are really close. You know, really close. So this is really good approximation. So let's just use I mean, it doesn't really matter what we use. Let's just use, for example, let's just use 6357, the polar radius, because this is really different, a tiny difference. Okay, 6357. That's the kilometer. So 6357. Okay, let's multiply by 10 to the third to convert it to meters, and then take square of that. Okay. Okay, so we have this combination. We have a really small number multiplied to a really large number and divided by a reasonably large number. Okay, so let's do this as an exercise together. So go ahead and take out your calculator and calculate this thing, and then send me a message. Tell me what you have. Okay. Now, a faster way to do that, you don't need to put all this scientific notation there. You can just do 6.67 times 5.97 divided by this thing squared, you know, and then multiply this scientific notation by itself. Okay, that'll be a little bit faster. Anyway, go ahead and do that. Okay, let me know when you're done. Okay, send me a message. Tell me your answer. Yeah, a lot of you guys, I don't know, you guys got the no, you need to use your calculator correct, you know. I mean, the reason I wanted to calculate this is kind of this is kind of like an amazing thing to do. You know, you discover something really interesting, you know, by doing this calculation. If you get it right, you know, you find out you get a number that's that we already really familiar with. So that's kind of really interesting, you know. Yeah, I'll give you guys maybe 1 more minute. Just try to get it right. So far I have one person get it right. Okay, I guess I'll just go ahead. I mean, this is just a calculation thing, right? There's no physics here. So so the way I did it was this. Okay, I take 6.67 times 5.97 divided by 6357 squared. Okay, so I did this part by myself, and then the other part is the powers. I'll just do it by hand. So it's going to be 10 to the minus 11th times 10 to the 24th divided by 10 to the third square, so 10 to the 6th. Okay, so this combination together, just like you're just adding 24 to minus 11 and then minus 6, so it's a negative 17. So this gives you together like 10 to the 7th. Okay. Well, this part, if you calculate by hand, by calculator, I mean, you get a 9.585 times 10 to the negative 7th. Okay. Again, I'm keeping 3 sig figures here because these numbers have 3 sig figures, so I threw away all the other numbers. So here I got this, right? So this 10 to the negative 7, 10 to the 7 cancel out. So in the end, I got something like this, m times 9.85, okay? Well, as I said, this number is something we already familiar with, right? So this is, remember we have this 9.8 here for the acceleration. Well, so why do we got this number? Yeah, well, if we use a little bit better number for the radius, we'll get exactly 9.8. But this number here, we're using the polar radius. Remember, the polar radius is a little smaller than the radius on the equator. So the answer you got would be a little bit larger than the actual answer. Like this one would be a little bit larger than the average, okay? But anyway, so let me kind of explain why you have this number here, okay? It's a very interesting thing. So remember the acceleration we talked about before, like we're saying when you're doing free fall here, all the objects falls with the same acceleration, that's 9.8, right? Why is that, right? So think about it. When the object is in the air, right, what kind of force does it have? There's only one force, which is the gravitational attraction. So we'll call this Fg here. Okay, there's only one force acting on the object. Okay, so according to Newton's second law, this force should equal to mass times acceleration of the object, right? But according to Newton's universal gravitational law, which is this one, you can write this force here as this thing here, Gme m divided by Re square. Okay, so that's the force you have, that equal to mass times acceleration, right? Now, one thing interesting you see here, the mass cancel out. There's a mass here and the mass here, they can be canceled out. If you divide m on both sides, m is gone. So your acceleration actually equals to this combination here, okay? So that's why when you calculate this combination, you get 9.8, because it should be 9.8, right? Because that's the same combination. It doesn't depend on mass because mass cancels out on both sides of this equation. And that's what we call G, right? We use lowercase g. And then as we see here now, this G is just equal to nothing but this thing, okay? This is a combination of 3 different parameters, okay? And we know it's equal to 9.8. Well, the last digit here, some people say 9.80, some people say 9.81. It's a little bit smaller than what we calculate here because we're using the polar radius here, not the average radius. So roughly it's 9.8 meters per second squared. Does that make sense to you guys? Yeah, I mean, it's really hard for me to tell because I only see, okay, I see some sums. Okay, that's better, okay. Okay, so based on this, right? See, now I explain where this number come from, why everything falls with the same acceleration. It is because of the combination of 2 laws of Newton's, one is Newton's second law and then Newton's law of universal gravitation. When we combine these 2 laws, we set up the equation, we see the mass cancel out. So the acceleration is a universal number. It's independent of the object, but only depend on the gravitational constant and then capital, the mass of the Earth and radius of the Earth, okay? Okay, I got some other messages, let me see. Okay, yeah, just some, I guess some other, okay. Okay, anyway, so this explains, so that's why we're talking about what we call it dynamics, right? We're trying to explain it by explain this one phenomena by using the Newton's law, right? Like the force. Because force is reason, and in this specific for a case, the force of gravitational attraction. So we be able to explain this thing. Okay. Now in the history, it is not how we got this 9.8. In the history, it's actually the opposite way. So, okay. In the history, what really happened, because after we realized this, right, based on this and this, after Newton, what people actually do is the opposite. So at that time, so history, what is known is actually the radius of the Earth, okay, and also G. Because these are really, I mean, the G is really easy to measure, right? Even we measured it, right, at home, you know, we got a pretty decent result. So people can measure G really well for a while, for a long time. While the radius of the Earth actually can be measured as well by using, like, considering the Earth as a sphere, and then consider like a pole on the Earth, you know, as the Earth rotates, this changes angle, etc. And then we can figure out from the shadow of the sun or something, they can figure out this angle, and then from there figure out the distance, and then figure out this radius. Anyway, so these two are, they can measure. But what we don't know, okay, is actually the gravitational constant G, and then the mass of the Earth. Well, as you can tell, it's very hard to measure the mass of the Earth, right? Normally when we measure mass, we use a balance, right? We put something on one side and then some weight on the other side. We balance them and we see how much it is. Well, certainly it's impossible to build a big balance. You can put the Earth on it, right? So it's really hard to measure it. Okay, so what happens is, in the history, is that there's a guy after Newton. His name is Cavendish. I hope I got his name spelled right. Maybe let me Google it. Okay. He's a Cavendish. Okay, pretty much right. So Cavendish is a Cavendish. Let me talk about Cavendish experiment. Yes. Okay. So yeah. So this guy, he actually this is performed like in the end of 18th century. So after Newton had died. But this is actually very, very interesting experiment. So this is the setup of the experiment. So the goal of Cavendish's experiment was to measure this G here, okay? Measure G, okay? As we see here, right, G is a really tiny number, like this 10 to the negative 11s, right? Well, but G is universal. So for any two objects, there's going to be gravitational attraction. So G is in there for anything, right? So what Cavendish did was he actually designed something really, really delicate, okay? So what he did was basically he has two metal balls hanging in there by a really, really thin like a string, like a metal string. And then he has some other weights, two other weights on the two sides that would, he put these two other weights there to attract these two metal balls. But this attraction, I mean, certainly, okay, like these ones here, okay, sorry, these ones. Certainly this attraction is gonna be so tiny, you know, because the attraction, as we explained, is very tiny, right? But this, although it's tiny, because the string is really thin, it's gonna, make a torsion on the string, so the string will be twisted a little bit, okay, tiny bit, okay? Well, that twist could be actually measured by using some light experiment, like an interference experiment of light, okay? So he could measure this very, very tiny twist of the string, and from there, he could deduce the force between this attractions, and then from there, he would be able to, he was able to get the capital G. So he was the first person that measured this capital G, okay, in the experiment, okay, like this. Now, after that, people know G, capital G, and also know the radius of the Earth and the small g. From these three numbers, they actually got this mg, okay, the mass mg. So they got from, so basically from this, you can see here, right? Based on this, you have me equals to g re squared divided by capital G. So if you know these three parameters here, you can calculate the mass of the Earth. So Cavendish's experiment was called the experiment of weighing the Earth, okay? Because after you figure out this universal constant, you can use it to calculate the mass of the Earth. So that's why his experiment was called weighing the Earth. And this is the first time people know how much mass the Earth have, okay? Again, it's not an easy question, okay? So, so it's very successful. But another comment I can make here is, see, there's a 2G we use here. One is capital G, right? We call it gravitational constant. The other one is this lowercase g, okay? It's just like called G, okay? This is a gravity due, acceleration due to the Earth. As you can see here, right? This capital G here is universal, you know? It is a constant, it doesn't matter what mass you have here, whatever, it's always same value. So that's a universal constant. Well, this lowercase g is not very universal. It depends on the mass of the Earth, the radius of the Earth. That means if you go to a different planet, or if you go to the moon, okay, because the mass and the radius are different, you get a different G value on those planets. It's not gonna be 9.8 anymore. For example, if you go to the moon, as we know, it's roughly, you get roughly 1/6 of this G there, okay? So this lowercase g is not universal, okay? The capital G is universal, okay? However, for our purpose, okay, when we do most of the problem we deal with are on the surface of Earth, okay? So in this case, we'll just use this, instead of using the full expression here to calculate the attraction, we'll simply take this combination and then we define as G. So we'll define a force called weight, gravity. We call gravity due to the Earth. We call it weight, okay? And it's defined as W, okay? And we define W as mg, okay? So mass times lowercase g, that give us, because lowercase g is nothing but this combination here, okay? So because of this, right? So we can replace this combination by lowercase g. So from now on, mostly in this chapter, we'll use this formula to calculate the weight of the object, or the gravity due to the Earth, okay? That's what we call weight, okay? It's the same thing. So I want to point out, this g here has unit of meter. See, this is 9.8 meter per second, right? It has a unit of an acceleration. But in this case, it is not a real acceleration, right? It is just a number to convert the mass to the weight, okay? So whatever mass you have is going to be in kilograms, and then kilogram times meter per second square gives you nothing but the force, which is in newtons, right? So this g here is, this is not a real acceleration, okay? Well, it is only the real acceleration when you have free fall motion, okay? When it's free falling, then it's a real acceleration. Otherwise, it's not, okay? Does that make sense, you guys? Again, I feel like it's really hard to tell, you know? Are you guys feel okay about this, or? Yeah, maybe whenever you feel like it, just give me some thumb up, you know? This way I can kind of see. Otherwise, I mean, because I cannot see you guys' face, you know, I don't really know whether you know it or not. Okay, so so this is just like conversion. So this also tells you like weight and mass are two different things. So see, weight is a force, and well, mass is just mass, right? So you need to multiply g factor to convert the mass to the weight. Well, your mass is kind of like universal. Your weight may not be. For example, if you go to the moon, as I said, you lose a lot of your weight instantly, because there's the g is really a way smaller number. So don't go to a you don't need to go to gym to lose your weight. Just go to the moon, you know. Well, it might be a little harder, but it may be like way faster. So next time you go to the moon, you can weigh yourself on the moon and then take a picture of that and put it on your Instagram or Facebook, and then people know, wow, he or she lose tons of weight, by doing that, So there's a difference in that. Okay, so that's the first force we talk about. Okay, so let me see. Okay, now what's the second one? So we spent quite a amount of time to talk about this force because it's a very fundamental force, and then the story interesting. So the second force we want to talk about is called normal force. Okay. So in this case, you have a let's consider like an object, right? You put an object on the surface. Okay. Well, this could be anything. Like again, in my case, if I put this object here, right? Well, as you can see, right, this object right now is staying at rest. There's no motion on the object, right? The object does not go anywhere, so it's staying at rest. According to Newton's second law, that means the force on the object must be zero, right? So because F equal to ma, if this is at rest, we have F equal to ma, so that means when if A is zero means that the force is zero, okay? The total force is zero. Well, but we know for this object, there is a force going downward, right? Which is our gravity. So I normally use mg for gravity, okay? Attraction from the earth, right? Our weight, there's a weight on the object. So that tells us that there must be another force balancing this force. Otherwise, this object is going to go downward with acceleration 9.8, right? So what is the force balancing this force? So in this case, it is the normal force, okay? And we call it N. And I mean, it's like the first letter of normal force. So we definitely need a force to balance this gravity. That's the normal force, okay? Well, what can we say about normal force, okay? So normal force always come from a surface, okay? And is always coming from the surface away from the surface. So you don't expect the surface to attract you, right? It can only repel you or kind of get you, push you away. So normal force, see the direction of the force is going away from the surface. The surface is right here. And it's also perpendicular to the surface, okay? So that's why the word normal in mathematics means perpendicular, So normal force you have is like whenever you have a surface, then you could have this force. You have a contact to the surface, and then it's gonna be coming from the surface and perpendicular to the surface. Okay. Well, we do not know the magnitude of normal force before we solve the problem. It's not a fixed number. It really depends on how much force you have going the other direction, right? For example, if you have this object right here, well, it is staying at rest, no problem, because the weight is balancing normal force. However, if you apply a force, like you push the object downward, right? The object may still, sorry, I need to turn it off. The object may still stay here at rest, but certainly there's a bigger force here going down because I'm pushing it downward. So in this case, normal force is larger. So normal force is something you don't really fix, it's not a fixed amount. It could change, okay? And also sometimes even when even the surface like this, you have vertical surface, you put an object here, there still could be a normal force. If you, let's say, if you push apply force to the object, kind of push it towards the wall, okay? You can certainly hold the object there, and that means there's normal force going backward, balancing this force. So again, in this case, it's perpendicular to the surface and going away from the surface. Okay. If you have a ramp here, same thing. There'll be a normal force going away. Okay. So again, what we can say is the normal force are perpendicular to the surface, and going away from the surface. Okay. Well, the condition is you have to have a contact to the surface. Without the contact to the surface, certainly you cannot have the normal force. Okay. So let's move on. So the third one I want to talk about is called tension. Okay. Again, this is a very easy force to understand, right? Using the same kind of demonstration here. Let's say you have this mouse here, right? You hold this mouse here, right? The mouse is staying at rest. Well, we know there is gravity going down, right? So there must be a force balancing gravity in this case as well. But there's no surface here. So the force is exerted by this string or wire or whatever you want to call it. And that is the tension. So whenever you have a piece of string or wire, this thing could exert a force on the object. And we normally use T for tension. Well, in this case, when the object is at rest, you have the tension balancing gravity, right? And again, what we can say is about the direction. So the direction is for tension is going along the string. It's kind of going, so it's kind of going towards the string. Towards the string. What I mean is like the string could pull you like this, but the string could not push you, right? It cannot apply tension going this way. It can only apply tension going that way. So going along the string and toward the string. So that's the tension. Okay. Again, the magnitude is not fixed. It really depends on what other force you have in the problem. Okay. Well, if the other force is too big, the tension may be broken, right? That's possible. And that, as far as it's not broken, that's actually determined by the other forces. Okay. Now, same thing here. the surface may be broken, may be cracked if you apply too big force here. But normally, when as far as surface is good, then the normal force is determined by other forces. Okay. So that's 15 minutes. Let me see. Let me finish maybe another force, and then we don't have time to do any examples today. We'll do it tomorrow. Okay. And remember, tomorrow we have the lecture starting from 9:45, okay? Because I have a workshop to go to at 11. So we'll do a lot of examples tomorrow, and you guys will have some time to do exercise tomorrow as well. And then on Wednesday we'll have our test. Okay. So number 4. So this is probably the last one, friction. This is again a very common force. And this force comes when you have again, contact with surface, okay? So let's first talk about kinetic friction, okay? So when you have an object here, right, you push it, it starts to move. But after a while, it stops. Why? Because there's a friction here. The friction will stop the motion, you know? See, it always stops, right? It stops because of friction, okay? So, and this is the friction when the object feels, when it's moving, so it's called kinetic friction, okay? So when the object is moving with velocity v, whatever, as far as moving, there's going to be a force going backward, okay? We call it Fk. K stands for kinetic, okay? So this is our kinetic friction. So this force, what the rho is trying to stop the motion. So eventually the motion will be stopped because of kinetic friction, okay? And so the direction of the friction is always going to the opposite direction of the motion. If the motion going to the right, the friction going to the left, okay? And so we have there's actually also a formula for the magnitude, okay? By doing experiment, people find out that kinetic friction can be written as this, mu k times n, where this is called coefficient of kinetic friction, okay? And this n here is the normal force, okay? So basically this formula tells you that kinetic friction is always proportional to the normal force on the object, okay? Well, you can understand this by again doing some demonstration here. So, say if you want to move this calculator, there's some friction on it, right? You can feel it when you move it. Well, you can understand if you apply a force, push the calculator downward, right? It's going to be harder to move the object because the friction is larger. In this case, by applying a force downward, you increase the force going down. So the normal force going up is going to be bigger as well. So the normal force becomes larger and the friction becomes larger as well. So, well, what about the coefficient here? So this coefficient here is determined by the surface of contact, okay? Determined by surface of contact. Okay, so anyway, so this is the formula for kinetic friction. Okay, but there's another kind of friction as well. It's called static friction. Okay. Now this happens when you try to, let's say you have a heavy object here. You want to move the object. You apply a force to the object, but the object does not move. Okay. Normally, as we understand, this is the reason that you don't apply a big enough force here. If the force is big enough, eventually the object will move. But if the force is not big, the object stays at where it is. Well, that is essentially because there's a static friction on the object. So it is the friction you have when there's no motion. So that's why it's called static friction. Okay, and this friction is the direction of that is actually so if you have a force like trying to move the object, and then the friction is going to go to the opposite direction. Okay, it's always going to the opposite direction of the external force. Okay, so opposite to the external force. This is, I don't know what is going on here. To the external force. Okay, so and also the magnitude, because this object stays at rest, so these two forces have to balance each other. So Fs here, maybe we can write like this, equal to negative F, where F is the external force. So it is equal in magnitude but opposite in direction. This way the object stays at rest, right? But as another thing is, it cannot go forever, right? If you have a force that's big enough, eventually the object is going to move. So that means there's a maximum value of Fx that you can have. It turns out the maximum value, you have another formula here. So it's going to be given by this coefficient times normal force. This is called coefficient of static friction. Okay, and well, it's similar to a coefficient of kinetic friction, but the value might be a little bit different. Okay, it turns out in a lot of cases, the coefficient of static friction is a little bit larger than coefficient of kinetic friction. Okay, and normally they're between 0 and 1. Okay. Okay. I guess that's all the force I want to talk about. Sometimes you were given some other force, like it's going to say that this box is being pushed by a force or pulling by a force. Well, that's just some specific force that they will provide for you, the details. But in general, there's this kind of force that you can have: gravity, normal force, tension, and friction. Okay, and I know this is for most of you guys, these are new, so it takes time to absorb them, to use them. To understand them. So we'll definitely show more examples, a lot of examples tomorrow and also on Thursday about using these forces, okay, in our problems, okay. And so for now, just keep in mind these two forces, okay. Those forces. So these are the forces we normally use to solve problems, okay, in this chapter, okay. So any questions so far? Again, these kind of theories kind of dry because we're just talking about these forces. Pretty abstract, but when we put them into problems, it is better. Okay. Well, one thing I want to emphasize here is there's an important way to kind of recognize all possible forces on the object. Okay. Well, I mean, this is actually a very important task. Remember, we want to use Newton's second law. For that purpose, we need to find out all the forces. Otherwise, we cannot figure out the acceleration. So how do we figure out force? This is normally called force analysis. Okay. So meaning that you want to find out every force acting on the object. Okay. So how do you do that? Okay. I would say always start from gravity. Okay. Start from gravity, because gravity is always there. Okay. And then after that, look for contact. Okay. Look for contact. Because all the forces we talk about except gravity are contact forces. Like see, normal force is only possible when you have contact with surface. Friction, same thing. You have to have contact with surface to have friction. Well, tension, you have to have it with contact with the string. So that kind of will include all the contact we normally have, either to a surface or to a string. So look for contact. Okay? The contact, whatever contact you have, determine whatever force you have. Okay. Well, and besides that, there's always gravity. Gravity is always there for the force. Okay. So we have 5 minutes left, but I think that's good for us today. So starting from tomorrow, I'm going to give you more, give you examples and everything.